Hi guys, in this lecture we're going to talk about random variables. So, what is a random variable? Well, let's begin with an experiment. So, if an experiment has numeric output, so it's some random experiment and the output is some number. So it has numeric output. We can call that a variable. So we can assign the output a variable name. And just by convention, this will always be capital. So, for example, capital X, capital Y, capital Z. So a capital by convention. And we call this variable a random variable. So we call this a random variable. And it's different from most variables you'll have encountered in math in that we never really talk about it having a particular value. You just talk about the probability of it equaling one thing or another thing. So let's look at an example. So an experiment could be that we toss a coin 3 times. So toss a coin 3 times. And now we have to get some number as the thing we observe. That'll be the output of this experiment. So there's obviously lots of different things you could observe and assign a number to, but in this example, let's take x equals the number of heads. All right. And so this is a number, so we can assign to it a variable, and it's a random variable because it's the output of some random process, right? So x is a random variable. And part of the reason for doing that is it makes notationally a lot easier to talk about certain things. For example, the probability of x equaling 0 is the probability that 0 heads come up when you flip the coin. So this is probability flipping all tails. Now it's obviously x equals 0 is a lot easier to write than flipping all tails, so in some sense it's notationally compact, which is nice. So that's part of the reason for doing all this. And we can compute that, right? So there's only one way of getting 0 tails, 0 heads, and there's 8 total ways you could do that. You could flip the 3 coins, so this is 1 out of 8. One might also ask, what is the probability distribution for this random variable? So what is the probability distribution of x? This is how this question would be phrased. And this is simply all the different possible values that x can have and what their associated probabilities are. So the way this is done is we would have a table. One way it could be done, right, where we say like k, and then across from that is going to be the probability that x equals k. So that's the header of our table. And so, well, the smallest x could be is 0, and we just computed that the probability of that was 1/8. if k equals 1, so then the probability of getting one head is, well, there's three ways to do that, right? It could come up in any single one of the three tosses. So that's 3 out of 8. And these are computations we've done a number of times now. We're just finally getting to the formal notation for this stuff. So k equals 2. Again, you're choosing, you could look at it as 3 choose 2 divided by 8, or where the tail goes. So there's also 3 out of 8. Then 3 is the last option. Of course, there's only one way to roll 3 heads. So it's 1 out of 8. Right, so this is the probability distribution for the random variable x. It's a pretty simple random variable, but it captures all the different things. Now, because the output is numeric, right, the other thing we could ask is, what does the histogram, the probability histogram, well, there we go, probability histogram of x look like? Well, is similar to plotting the histogram for data, except for now it's a theoretical probability histogram, and so instead of the quantity of each value, we plot the probability. And I should note, this is fairly important, but the way I'm showing you how to make a probability histogram, this only works if our random variable x, so this only for random variables that take on only integer values, that take on integer values. Okay, so what I'm showing you, you'd have to modify it slightly if you had a more complicated situation where it could take on, say, half integer values or something like that. But we're really only going to deal with random variables that take on integer values, so this method will work. And the method is simply that we plot each value with its probability. Let's say, so we have 0, 1, 2, 3. And then around each value, I'm going to make a bar with height equal to the probability. So let's say this is 1/8, this is 2/8, and then this is 3/8. Right, so around 0, I'm going to make a bar of width 1. It's going to go here. I'll go up to 1/8. Around 1, I make a bar also of width 1. It goes up to 3/8. And the same thing around 2. Then around 3, again, I have a probability of 1/8, so it goes up to 1/8. Alright, so we've plotted the probability histogram for x. We could label this axis x. So what's nifty about a probability histogram? Well, it does give you sort of a visual depiction of the way the probabilities are clumped. You can, 1 and 2 are higher, 0 and 3 are, less likely. But one nifty thing that we did, so notice the widths of the rectangles are 1. And what that means, this means that, so if a rectangle has width 1, right, so these are all have width 1, if a rectangle has width 1, then its area is equal to its height, right, because the area is height times width, and width is 1, so it's just height times 1. So this means area of rectangle equals height and thus so probability that x equals k, well, this is just equal to the area of the rectangle about k. So for example, if I take an orange, so probability x equals 2, well, that's the area of this rectangle here, equals 3 over 8 times 1 equals 3 over 8. And this is really what makes it a probability histogram, is that somehow the geometric area corresponds to probability. So that is the key thing. And this is, now, the way I made the plot only works if we have integer values, but you can have histograms in general for things that aren't just integers. And the thing that makes it a histogram, the key thing, is that the probability of some event corresponds to area, the geometric area in the histogram. So general, so we have the correspondence. Area in histogram and probability. And that's, well, that's pretty cool. So, for example, if we wanted to compute probability of x less than 2, we would simply look at, we'd sum up the areas for all the rectangles that correspond to values less than 2. Right, and that is, so this is an eighth plus 3/8. So this equals 1 over 8 plus 3 over 8 equals 1/2. Okay, so that's the histogram associated with the random variable. And the sort of the final thing you might ask about a random variable, to continue with our bulleted list, is what is the median value of this random variable? So what is median of x? So there's really two ways to do this. Let's do the simplest way first. So method 1. Unfortunately, method 1 becomes slightly impractical, but at first it's definitely the most straightforward way. So we simply take the median of a perfectly representative sample. What do I mean by that? Well, you could imagine conducting the experiment a number of times, and you get some ratio of outcomes for the different things. They wouldn't necessarily align with the exact probabilities. But we can, knowing what the probabilities are, we can construct sort of a set of data that perfectly matches with the probabilities. So in this case, for example, we would have 1, 0, right? Because there's one way of that happening. 3 1s, there's 3 ways of that happening. 3 2s, and then 1 3, right? So the frequency of 1 here, so what's important is that frequencies match probabilities. Right? The probability of getting a 1 is 3 out of 8, and the ratio of the number of 1s to the number of data points here is exactly 3 out of 8. It's exactly the probability. And so then we can take the median of this data that matches the probability. So in this case, there's an even number, so we have 2 middle values, so median equals the average of 1 and 2, which is 3 over 2. So this is the median of x, sorry. Equals 0 over 2. So the other way is kind of like using the histogram to compute the median. And this can be useful if you have essentially if the denominator of your probabilities is very large, so that constructing a perfectly representative sample would be very, very long. It's essentially, it's the same rules for taking median. It's just a slightly different way of thinking about it, which is so go from left to right, and you could do this from right to left also. I'm just essentially choosing one. Go from left to right on the histogram. Accumulating area. Essentially just add up the area of the successive rectangles from left to right until one of two possible outcomes happens. Until 1, you hit 50% exactly. So you hit 1/2 exactly. So you hit 50% exactly. If that happens, then you essentially have two middle outcomes and you take the average. So, and then take average of the two middle outcomes. The other possibility is that you never hit 50% exactly as you're accumulating these areas, and instead at some point you go from less than 50 to more than 50. So we'll call that you pass 50%. So you pass 50%. And of course we're going to do examples of all this in just a second. Pass 50%. And then take the last value as the median. Right. And if you work these out and think about it a little bit, you'll see that these methods are really exactly the same, and they'll always give you the same value. This is just, I don't know, it's just two ways of approaching this calculation, essentially. All right, so now let's do some examples. I'm going to insert this file. Come on. All right, it's a little slow. All right, random variables. Well, I hope. Alright, here we go. Alright, consider the following histogram, probability histogram for the random variable x. Alright, so x takes on values between 0 and 5 inclusive, and we want to calculate the probability that x is greater than 2 and the median value. So the first part is fairly simple. So the probability that x is greater than 2, let's use orange. This is going to correspond to the rectangles associated with the values greater than 2. So it's the area of these rectangles. And right, the rectangles have width 1, so their area is simply their height, so we add them up. So this equals the height at 3 is 0.3, 0.3, plus the height at 4, which is 0.2. And the height at 5 is 0.1. So this adds to a 0.6. So there's a 60% probability that, probability of x is greater than 2 equals 0.6, or 60%. Right, so the next thing to do is to look at the median. Now, it wouldn't be too hard to construct a perfectly representative sample of this random variable. All the denominators are out of 10. There are 0.1, 0.2, or 0.3, these values. So we'd only need 10 samples to construct a perfectly representative sample. But I want to illustrate what I was talking about earlier. So I'm going to go from the left to the right, and I'm just going to add up the values of the rectangles until I get to either exactly 50% or I just pass 50%. Alright, so here, so if I'm looking at everything 0 and below, that has probability of 0.1. If I look at everything, if I go one rectangle over and look at everything, now these two, right now I have 0.2. If I accumulate the next rectangle, now the total area here that I've accumulated going from left to right is, well, it's 0.1 plus 0.1, which is 0.2 plus 0.2 is 0.4. So I haven't cracked 50% yet. I haven't hit it exactly or passed it. And then at 3, if I include the rectangle around 3, right, what do I get? Well, I get 0.3 plus everything I had before, which is 0.4. So I get 0.7. So here we get 0.7. So in the language of probabilities, right, we have probability x less than or equal to 0 equals 0.1. Probability of x less than or equal to 1 equals 0.2. Probability of x less than or equal to 2 equals 0.4. And then if I include the next one, probability of x less than or equal to 3 equals 0.7. So this is where we pass 50%. And so therefore, median of x equals 3, because that was the key value. And note, if we worked from the other way, if we worked from right to left instead, we would get the same thing. Right, 0.1 plus 0.2 is 0.3. You add it, that's less than 0.5, and then you add, so going this way, right, it's these two sum up to 0.3, adding another 0.3 passes 0.5 to get you to 0.6. So it gives you the same value. The median of x is 3. Okay, there's that. Now let's consider the next example. So consider the experiment of rolling a die. Let x be the number rolled. Alright, there's a nice experiment with a numeric outcome for sure. Draw the probability histogram for x and compute the median value. Alright, I guess I'll stick with blue. Well, so the first step, if you want to draw a probability histogram, is we have to know what the probability distribution is. So come up with a table of values and their probability. So step 1, find probability distribution. Alright, so in this case, it's not so difficult, right? I didn't say anything about an unfair die, so we can assume that it's a fair die, so all outcomes are equally probable. So we have k, and the probability that x equals k. Alright, so we have 1, and that has probability 1 over 6. 2, that has probability 1 over 6. Everything is equally likely, so they're all probability 1 out of 6. Right. So that's our probability distribution. And we use that to draw the histogram. Right? In this case, it's a pretty simple histogram. We have 1, 2, 3, 4, 5, 6. And again, we need to put rectangles of width 1/2 about everything. And they're going to go up to the value of 1/6. Everything is just as high. So I'm just going to draw one big fat rectangle. And then we can put divisions in if we really feel like it. Okay, there's our probability histogram. Oops. So that's our probability histogram. And it asks us to compute the median value. So again, it wouldn't be too hard to come up with a representative sample. In fact, since everything is equally likely, just one of each is a perfectly representative sample. But let's show what I mean by the accumulation of areas. If you find this method to make sense, then that's great. If not, you can go with a perfectly representative sample. So we accumulate areas starting from the left to the right. We have 1/6. Right, and we add the next one, we get 2/6. Which is a third, obviously. Then we add the next one. We get 1/2 exactly. So we hit 1/2 exactly. So in other words, we can split the histogram right in between 3 and 4, and we get 50% on one side and 50% on another side. So let me write that down. So splitting right between 3 and 4, we have exactly 50% on each side. So we have two middle values. Three and 4. So we take their average. So median of x equals b plus 4 over 2 equals 7 over 2 or 3.5. And that's exactly the same as if we looked at one of each value, which was a perfectly representative sample. which is an even number, and so then the median is the average of the middle two. Right? Same thing as looking at the histogram to do it. All right, so that's that. I guess see you Monday. All right.